Hey, let's learn how decision trees work. So in this video, I will be showing you how they work on a technical level, kind of on the background, how does the learning and training happen, and then I will be making a follow-up video where I will tell you how they work and also show you how we can implement them in Python using scikit-learn. And this is actually one of the algorithms that I use on my course, Hands-on Data Science. So if you're interested in learning how we can use decision trees on a real-world data set, go and check that one out. But without further ado, let's get started. All right, so let's learn about decision trees. How do they learn? How do we train them? How does the whole mechanism work? So basically, decision trees are kind of like how we decide to do something. For example, take an umbrella with us or not. You know, let's say we are trying to decide it, and then we can think, okay, is it raining or not? Because if it's not raining, I don't really need to take an umbrella with me. If it is raining, then I can start thinking about, okay, how long is this walk? Am I going to walk for a very long time? Because if not, maybe I can just make a run for it, you know? And another thing that I can think of, okay, if I'm going to walk like kind of like a in-between distance that's not going to take me too long, but also not too little, then I can think of, okay, do I need to look nice where I'm going? You know, if it's like I'm going to the movies with my friends, maybe it's okay if I look a little bit wet, but if I'm going to a nice dinner with my, I don't know, girlfriends or boyfriends' parents, then maybe you want to look nicer if you're like doing makeup or doing your hair, for example. So of course, how does this happen? We create this tree based on a data, right? So let's say we have a set of data. One column could be, is it raining? Another column could be the length of walk. Another column could be the event index. I mean, I'm thinking of it as like, how nice do you need to look index? Like if it's 0, then you don't need to look nice at all. If it's 10, it's definitely a place where you need to look super nice, let's say. And umbrella decision. Let's say this is my kind of like data set. And you know, it could be that, so you're basically basing this decision on your previous experiences. So let's say there was one time that it was raining, you were only going to walk 200 meters, and you didn't really need to look so nice. So then you didn't bring an umbrella. There was another point where it was again raining, and you needed to walk 750 meters, and you kind of needed to look nice. Let's say if it's like an event index of 9. I'm definitely making this up, by the way. And then you didn't bring an umbrella. And there was a time it wasn't raining. You only had to walk 500 meters. Let's make them meters. And it was kind of like an in-between event. And then you didn't bring an umbrella, obviously. And another event, let's say, where you had to walk like 1,000 miles, 1,000 meters, 1,000 miles. And it was like a nice-ish event. But you didn't bring an umbrella because it wasn't raining, right? So that's an easy decision. So this is like one example of a data set that this tree might be based on. But of course, you know, it's very simple. In this case, it's very intuitive. But let's look into how these trees basically work. You can also call this a pseudocode. If you never heard of this term before, it's basically like very high level instructions of how the training will happen or how the tree will be created. So in the case of decision trees, what happens is you say, so you have all these columns, right? And this is a target column. This is what you're trying to decide. You might have more columns, of course. Decision trees are very good at deciding which columns to include or not, because if a column is not contributing to the decision process, it will not include it. So that's something important to know. Yes. So basically what happens is, on the first step, the decision tree chooses the best column, or let's say feature, and it will make it the beginning feature that we will be deciding. I think in some places this is also called the root. So that's the first thing that it does. And the second one it does is create the split based on this feature. So basically what happens is here it decided that it's going to go with is it raining, right? And here it's this one. So then it says it's either is it raining, the answer is yes, or the answer is no. So basically what happens is it sends all the data points where the is it raining question is answered with a yes here, and all the ones that are not answered with a yes here. So yeah, so as you can see, when it's a no, it's definitely don't take an umbrella. And yeah, and these are the answers. And what happens is then it basically repeats it all the time, choosing the best one and the best one and the best one after another. And the last one is, okay, how do we stop? It basically stops when the leaf nodes are pure. Okay, so I'm pretty sure already a bunch of questions popped up for you. So let's answer them one by one. Okay, what does it mean, the leaf node? The leaf node are the nodes that are all the way at the end. So, I mean, of course, this decision tree looks like it's going down. But if you think of it as like a tree where the root is here and these are the leaves, so like turn it upside down basically. These are what are called leaf nodes. So like, you know, all the branches go up and then at the end you have leaves. A leaf node being pure means that you only have one value. So it's here we're working with 0 or 1, right? So it's like, for example, this one, it divides it from yes or no, and like this one. When you go with no, this is pure because there is no other answer. It says if it's not raining, do not take an umbrella. So this leaf node is pure now. But here, when it divides it with yes, what happens is you still have some options, the possibility of it being yes or no. So it's not pure yet. You have to divide it further to get pure nodes. So this is a good thing to know. These are some just like general 3 terminologies. But of course, there are some other questions that we want to ask at this point. So for example, let me mark it with other colors. What does it mean to be the best feature? How does it decide that something is the best feature? What happens when the split needs to happen with a continuous variable? So here we've only seen, for example, the first one that we've seen is either 0 or 1, right? What happens when it's a continuous variable like this? Because this can be any value. This doesn't have to be 200, 500, or 1,000. It can be 758, right? So how does it decide these values, 500 to 1,000, or 1 kilometer? So that's the second question. This is the first. This is the second. Not the best clarity. And the last question is also, how does it do the split when there is more than one categorical value? So, you know, this could be an example. The event index could be an example for this. I mean, we don't really see it in the tree here. We kind of think of it as like, you know, this variable has been divided into either yes or no. But when you think about it, then you don't only have zeros or ones. You have, if you think of this as like categorical events, you know, you can also kind of like have it as, let's say, we can say, oops, this means dinner. This means, I don't know, theater, going to the theater. This means chill with friends. And this means picnic in the park. So then these are different categories that we need to consider. And how does it make the split when how does the tree make the split when there are categorical and more than 2 categories involved? And as a last question, we can ask, what is the difference between approaches of classification and regression? So what is the difference between classification versus regression, and how do they happen? So this is yet another question that we want to answer. So let's start one by one and start answering these questions. All right, so let's start with our first question. Our first question was, what does it mean to be the best feature? So if you remember, I said that we make the splits in the data set based on which feature is the best. And this is basically where we come to a crossroads to an approach to decision trees. There are a bunch of approaches out there, but the main ones that are being used by the scikit-learn algorithm, the scikit-learn library, is called CART or ID3. So as far as I know, CART1 is the default one. So if you start using scikit-learn out of the box, you will be using CART. And but if you want, you can also use ID3. That's also a possibility. So let's just put a little star here to show that it's the default one. So how are they different? Basically, they are different in how they determine which feature is the best one. So the CART algorithm is using something called the Gini index. And the ID3 algorithm is using entropy. So I will not go into the details of how we calculate these things, but basically entropy is a measure of randomness. If you ever taken a chemistry course, maybe back in high school, you might remember it from chemistry. It's basically the same concept of how things are random. So let's say a coin toss, for example, I think is a very common example that's given because the chances are 50-50 that it will either be 0 or 1, then the entropy is basically at its highest. It's, it cannot get any more random than this. The more certain that you are that it's going to be one class or one outcome, one certain outcome, the more the entropy is lower, basically. For Gini index, it's also called impurity. Let me also note that down. And Gini impurity is a measure of how pure the resulting nodes will be after the split. So if you manage to split a data set into two perfect sets, so let's say one branch or one leaf node is going to have only one class as a result, and the other one is going to have the other one, then you will be totally pure, right? So that will be a totally pure result, and that will give us a low Gini index. And on top of entropy, we also calculate the information gain. Let me just quickly show you how they're calculated, kind of like their formulas, but I don't think you should really be scared of this because it's actually pretty simple to calculate. I will also leave links to two of the articles that I found online, which I think are very useful. So I don't want to go through how this is all calculated and everything, but I think if you follow the examples there, you will have a really good understanding of how entropy and Gini index works. So basically entropy, as I said, is just randomness, and this is how it's calculated. It's basically like the P's are the probabilities of each different category. Same one for Gini index, it's again the probability of a certain category. And information gain is calculated as what is the entropy before we do the split and what is the entropy after we do the split. And for Gini index, we mostly calculate just what's going to happen, what is the purity is going to be after the split. The main difference that you need to know here is the Gini index only separates things in a binary way. So it cannot make trees that have nodes that have branches that are more than 2. I think that was a very complicated way of saying it. So Gini index only creates branches like this. So it's either yes or no. But with entropy, with the ID3 algorithm, you can actually have more than 2 possibilities. So, if you have some categories, let's say in your data set, it could be that, category A goes here, B goes here, C goes here. You cannot do that with the Gini index. So that's the main difference. Not one of them is objectively better than the other one. There are upsides and downsides to using each. But yeah, we'll see more about how to implement this also in the next video when I'm showing you how to implement decision trees with scikit-learn and Python. But as you might realize, these are basically greedy algorithms. So what happens here is every time they look at all the features that are in the data set, like the example that I showed in the previous page, and they look at all the features, they calculate the Gini index and the entropy for both of for all of the features or columns that we have for all the splits, and they decide which one has the best entropy or information gain, or which one has the least impurity, right? So it is not thinking, okay, but what if I choose the other one and then this one and then the other one in the future? So maybe choosing a feature or column that has a lower information gain will help you in the future. But then that problem becomes very complicated. So that's why decision trees do not use this approach. They just use greedy approaches. Because if you try to think of all the possibilities of like choosing, let's say, column A, and then column B, and then column C, you're going to get into really complicated territory, and the complexity of your algorithm is going to be very high, and it's going to take you a very long time to learn a very simple data set. Or fit a very simple data set. But with the greedy approach, it actually creates maybe not the perfect tree. Maybe it doesn't find the global optimum, but at the end of the day, it gives us a good enough representation of the data set that we're doing pretty accurate predictions, let's say, on our data set. So that answers our first question, how do we choose the best one? Basically, we either calculate the entropy or the Gini index on all the features, and we choose the one that gives us the least impurity or gives us the most information gain. And the next question that we had was, how do we do this for categorical columns that have more than 2 categories? So as you can see, for entropy, we can have more than a binary split, so that's fine. But let's say we have 4 or 5 values for a feature. So, I mean, if I need to show it as like a data set, maybe this is feature 1, and we have a feature 2, and then we have the target variable, right? Let's say the feature 1 has like A, B, C, B, A, C. Let's say it can be anything. Feature 2 could be, maybe it's like just 0 or 1. So, and target variable can be anything. So how do we decide where to do the split for the Gini index? What happens is you can calculate the Gini index. You're going to have to calculate Gini index for feature 1 and feature 2 to see which one it will bring you a better purity. But you can also calculate it for each of these. So basically you're just getting and seeing what will happen if I separate it as, is it A or not? Then this will go all the places where the data point has the feature 1 value as A. So you'll be getting this one and this one, and then you'll look at your results. Okay, what is the purity? So it's like A against everything else. And then you can calculate it for B against everything else, and then C against everything else, and then see which one brings you a better purity or less impurity, and then select it that way, basically. So that's how you do it. Another question that we had was, how does it work when you have a continuous variable? So let's say, let's create another one again. This is one, and let's say we have the target variable, right? We can say we have like 2, 4, 6, 8. Let's see them as kind of sorted. Let's say these are the values that we have. I made it very easy for me mathematically. But what I learned is actually it's very neat. So these are the data points that we have, right? And when you want to find a point where you have to, when you want to divide it to make that decision. So say, if it's less than 5, then go to this side. If it's more than 5, go to this side. How do they do that? Is they calculate the average of the values. So they say, let's say this is 3, this is 5, and this is 7, right? And then you calculate the entropy or the Gini index, thinking what happens if the feature 1 is 3, and calculate the values and then see and compare it to what you calculate when the feature 1 was 5, or less than 5 or more than 5, and do the same thing for 7. So you're basically creating some cutting points for yourself, and then choosing and trying to see which one will bring you more information gain or more purity. And then you can decide and then say, okay, I want to divide this as like, is it less than 5? If it is less than 5, go here. If it's more than 5, go here. Everything we've seen so far was how the classification algorithm would work with decision trees. But we also want to do regression with decision trees, right? So here in the screen, you're seeing a feature and how it corresponds to the target value. So if this feature is 1, the target value, let's say, is 2. If this feature is 8, the target value, let's say, is like 15, right? So this is one way of showing how the feature corresponds to the target value. So, you know, what do we need to do? Again, we need to choose the best feature. We need to choose the best feature to do the split. And how do we do that? We compare the information gain normally of different features. And here we're going to choose the feature that gives us the least error. But how are we going to do that? And how do we know? Do we have to separate it here? Do we have to separate it here? Do we have to separate it here? Like, how do we decide that? So the first thing that we need to do is to decide the cutting point for this feature. So how do we do this? We basically create a lot of cutting points possible, or potential cutting points. It could be one, this could be one, this could be one, you know. So let's say these are all the possible cutting points. And then what you do is you compare these cutting points to each other. So let's say this is cutting point 1, 2, 3, 4, 5, 6, etc., etc. So then I will say cutting point 1, cutting point 2, cutting point 3, cutting point 5, and then this goes on and on. Then cutting point, I don't know, let's say 15. All right. So what I do is for each of these points, this can get a little bit confusing, so I'm going to try to go slow here. I'll show you with the example of 4. So this is one cutting point, right? For each of these cutting points, I'm going to say everything that's lower than this cutting point, where the feature 1 equals to 4, is going to get the value of average of everything that's here. So average of these guys here, right? So let's say the value here is 5. So I'm saying I'm going to make I'm saying one possible way of dividing is I'm going to say if feature 1 is lower than 4, I'm going to make the division or the split lower than 4, yes, then the answer is 5. If it's higher than 4, I'm going to say, well, my prediction is, let's say this corresponds to like 30. So this is going to be 30. Then I'm going to say, okay, then my prediction is it's going to be 30. That's what I'm trying to say here, basically. If it's lower than 4, my prediction is all of the average of all of these guys, and that is 4. So that is 5. And if it's higher than 4, then my prediction is the average of all of these guys, which is, let's say, 30. All right. But how am I going to compare the cutting points to each other? So I'm saying this should be 5, right? Then I can basically, at this point, calculate the error that I get. And how we calculate it is basically we get the sum of squared errors. And I'm looking at the error here, 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 here. And then this is going to amount to an error value, let's say 1. Or this is cutting point 4, so let's say this is error 4. And again, I'm going to get the sum of squared errors here, here, here. All of the error values, I'm going to get them. And then basically together, they're going to give me an error value. And let's say, no, this is not it. Here, error 4, right? And for each of them, I'm going to calculate the error. Like if I divided it at 1, what will be the error? If I divided it at 2, what would be the error? If I divided it at 3, what would be the error? So on and so forth. So then let's give these like random numbers for now. And okay, then I calculate the error for thinking what happens if I divide it here, happens if I divide it here, what happens if I divide it here. And I am choosing the cutting point that gives me the lowest of all errors. So here it's this one, right? So apparently error cutting point 4 is giving me the least error. So then I'm saying basically going back one level higher, because we're doing this to compare features to each other, right? So if the data set looks like this, there's feature 1, there's feature 2, there's feature 3, and then the target variable. And I'm trying to choose which one to do the cut on, and also where in the feature should I do the cut on. Then I will say, okay, for feature 1, error 4 is the lowest, and it's this much. Okay, so if I cut on error 4, this will be the error. And then I'm going to do the same thing for feature 2. Well, if I cut on feature 2, this will be the error. If I cut on feature 3, I look at all the possible options, and then this will be the error. Then I can easily say, hey, it really looks like feature 1 is the best option here. And on feature 1, I'm going to say cutoff point 4 is the best option. So we learned how decision tree algorithms work, but there is one more really important thing that we need to understand about them, and that is that they tend to overfit. So if you haven't learned what overfitting is, and if you want to learn more about it, I will leave a link to my video where I explain what overfitting is. But generally what happens is, let's look at this example data, and how you would normally divide it would be something like this, right? So yeah, maybe you are going to mispredict this data point, and these data points. But at the end of the day, your goal is to generalize based on the data set that you have. You're not trying to perfectly fit the data set, because the data set that you have is just some observations collected from the real world. It doesn't perfectly represent real world. But what happens when you overfit is that it will look something like this. So you're really trusting the data set that you have, basically, and you're saying, okay, this is a very rigid decision boundary. But this can cause a lot of problems, and this is something that we don't want. We want to make sure that we're generalizing. How do we solve this with decision trees? Is one thing you can do is pruning. So this is pretty common to do. It's basically when your data, when your decision tree goes like this, it goes all around, and then maybe like this. So it becomes like a gigantic decision tree. Then what you can do is basically there are algorithms to do this, but basically you're like looking at which branches are not actually giving you so much information, and then you'll just say, okay, let's delete this one, and this one, and then basically make your tree a little bit smaller. It is not going to perfectly answer or predict all the data points or all the examples, but at the end of the day, you're going to have a better machine learning model in your hands, because it will not be overfitting your data set. Another thing you can do is setting up stopping criteria. So as I said in the beginning, normally the algorithm is to run the decision tree algorithm until all the leaf nodes become pure. So they only have one type of data point in there. But instead, what you can set is you can set some other stopping criteria. So And this stopping criteria, we will learn more about this in detail when I'm looking or showing you how to do this in Python and scikit-learn. But basically you say the depth of the tree, which is basically like, that this is the 0th step, this is the first, second, and third, and as it goes like that. You can say the depth of the tree can maximum be 4. For example, that's just one example. So these are some ways to stop the growth of the tree before all the leaf nodes become pure. And that way you can really stop overfitting. And the last one is ensemble methods. So this is where basically you stop doing a decision tree. If you ever heard of it, there's this other algorithm called random forests, and with random forests you are bringing together a bunch of decision trees, and in that way have them generalize better. It's an overall a better algorithm generally to do predictions in a complex data set. So this is the last version. This is the last option of how you can approach decision trees to kind of make them overfit less. But one last thing that I want to show you also after overfitting is, why would you choose to work with decision trees, or why would you not? So the disadvantages of decision trees is, the first one is that they're very sensitive. If you change the data set that you're giving it, it's very likely that the tree is going to change. So you're not going to get the same tree every time you give it more or less even the same data set. So that's the problem. They're very sensitive, and they very base the whole model on the data set that they have. And generally the decision boundary tends to be very stiff, and this kind cause overfitting. So that's where you have to be very careful and make sure that you're generalizing well before going forward with decision trees. But there are some advantages, of course, to decision trees. So one of them being they're very explainable. So this is not always something that you're going to use, but even if you wanted to, most of the time, I'll show you again this in the Python lesson or Python video too, you can really get like a tree showing you how the decision works. This could be a really big tree, of course, if you're doing if you have a big data set, but if you really wanted to, you can visualize your model and you can really see how the model makes its decisions. So in comparison to other machine learning models, which they're like black boxes where you don't understand how it makes its decisions, this is a really good opportunity that you have with decision trees. Another good thing about decision trees is that it can do classification and regression, so that makes it very powerful. And basically, it just is capable of fitting complex data sets. So that's something that we really need too. And last but not least, they really require very minimal data preparation. You don't have to do any standardization of your data set or a normalization of your values. So you can nearly use it out of the box and just like put your data in there and see what comes out of it. And it does feature selection for you. So it doesn't select the features and doesn't have them in the algorithm or in the model if they do not add anything to the decision process. So that's something that's really good about decision trees. So yeah, this is all about decision trees and how they work in the background. And in the next video, we will be looking into how we can implement it in Python, what are the options, and also maybe even how we can visualize decision trees. So I'll see you there.